I will soar, then, beyond this power of my nature also, still rising by degrees toward him who made me. And I enter the fields and spacious halls of memory, where are stored as treasures the countless images that have been brought into them from all manner of things by the senses. There, in the memory, is likewise stored what we cogitate, either by enlarging or reducing our perceptions, or by altering, one way or another, those things which the senses have made contact with. St. Augustine, Confessions. When most people look out at the waves on a beach or up into the sunset, I imagine their thoughts are geared towards the beauty and majesty of nature. The colors, the sounds, the smells, those almost physical, tangible feelings that make up that memory. But if you're anything like me, you'll also think about the unknown, about what hides beneath waves and above clouds, what is tucked away from view. Maybe you're overcome with curiosity and want to find out more, or maybe feel afraid of the unknown, or maybe it's a bit of both. I think of that quote by St. Augustine as my experiences are brought up to my memory by my senses. What I see and feel and hear, those are anchors of experiences that later form memories and develop curiosity and questions. For me, this drive to uncover what is hidden by green waves and white cloud cover is what fuels my ambition, and it has done the same for many before me. While not everyone's first instinct upon seeing the ocean or the night sky is to go towards and into it, mine is. I want to know what is there to be seen and known and discovered and collected as a treasure in my memory. Fortunately, I am not alone in this desire. Many explorers and researchers and scientists have paved the way forward, exploring the Earth, its oceans, and its atmosphere. But how do they do this? How do they overcome nature's inherent intensity and hostility and go boldly forward into environments that, without the assistance of technology, humans would never be able to go to? Part of that is their drive and curiosity, but the other part is brilliant technological innovation that has allowed humans to sustain themselves in extreme environments. When most people hear the term extreme environment, I imagine they think of places like the deep ocean and outer space, both of which are archetypes of the unknown, and of places that are inaccessible to humans. The sheer amount of effort required to send even one person to places such as these is immense, and yet people go and work and live in the ocean and in space. My field of study, human systems, is concerned with any kind of system that has a human element. This includes anything and everything from assembly lines to computer interfaces. The study of the human components of technologies makes up the foundation of human factors, a subfield of human systems. Without this field, the technologies that support human life in extreme environments would not exist. Spaceships and submarines must be designed with the human element as the central focus. So, in this video essay, I will explore human factors' impact on technologies in extreme environments. I will present important context and 2 case studies of outer space and deep-sea vessels that have allowed intrepid explorers to, well, soar beyond the power of their nature and store up treasured memories through experience, then return and share with the world what they have seen in the places where most of us can never go. Human factors design considerations in extreme environments. Chapter 1. What is human factors? Human factors studies the interactions of people and the systems with which they work. The goal of human factors engineering is to create systems that are easy for people to interact with. That is, they reduce user error while increasing comfort, productivity, and safety. The Human Factors and Ergonomics Society, a professional organization for human factors specialists, further defines the practice of human factors engineering as the design of systems based on scientifically derived data on how people perceive, think, move, and act, particularly when interacting with technology. This field is all about the intersection of humans with their environment. Human factors is an immensely broad and interdisciplinary field. Its overarching goal, however, is to design systems that put the human user's needs first. This is called human or user-centered design. But what do we even mean when we say design? Design is, in itself, a very broad topic, but in the context of this video, I'll refer to design as the process of creating safe and ergonomically sound systems. Here, ergonomics refers to the physical aspects of human-environment interaction. An early focus on the user can make it easier to create a system that supports the user, rather than making something for them to adapt to. It starts with the identification of user preferences and requirements. While this may sound simple, it's actually a fairly involved process. In this, the overall goals of the system are identified. Then users' key needs and preferences that correspond to each system goal are determined. Because these lists of features and preferences can get quite long, it's also important to weight them in terms of priority. This process creates a list of system specifications, including the system's overall goals, performance requirements, and design constraints. However, there is another element of system design that is important to human factors: safety. Safety is the prevention of injury or death-causing situations. Because one of the broad goals of human factors engineering is to increase the health and safety of people in all types of systems, accident prevention is a major concern. This begins with the identification of risk. Risk is the combination of the probability and severity of an event. Critical hazards, those with high probability and high severity, are best dealt with by designing them out of a system. Lower-level hazards can be controlled through safeguards. Risk management is all about balancing system functionality with safety. Human factors specialists must also follow regulations to ensure that systems meet an objective safety standard. They do this by consulting standards, guiding documents that establish technical requirements, specifications, and procedures for many different conditions. During the design process, human factors specialists must ensure that each function of the system meets user-specified requirements, safety standards, and also falls within the range of human capabilities. These kinds of design considerations include the physical capabilities of human beings, like visual and auditory systems, but also their psychological and cognitive functions as well. These are each in their own right very complex topics, but to give a brief summary of what factors are considered in human factors engineering, let's take a brief look at these.
Visual. Visual components of a system include the limitations of the eye and neural pathways that send messages of visual information to the brain, as well as the processing of these signals by the brain. The limits of the human visual system influence the nature of the information that arrives at the brain, information that is then used to make a decision or interpret other information. Auditory. The auditory components of a system refer to the ability to process acoustic information and the influence of this processing on performance, health, and comfort. This is related to the auditory experience, the physical part of human speech, background noise, and sound transmission. Tactile and haptic. Lying just under the skin, sensory receptors that respond to pressure relay information to the brain about force applied by the fingers, hands, and other parts of the body as they interact with physical things in the environment. These receptors also describe the shape of manipulated objects. These senses are extremely important to how people interact with and gather information about the world. Tactile and haptic factors go hand in hand with the next group of considerations: proprioception and kinesthesis. Proprioception is a set of receptor systems located within all the joints of the human body that relay information about joint angles and limb position. Closely related is kinesthesis, the sense of motion of limbs as exercised by muscles. Collectively, these two senses, along with tactility and haptics, provide feedback for everyday movement and interaction with objects. Vestibular. Located deep within the inner ear, vestibular receptors convey information to the brain regarding the angular and linear accelerations of the body. Try this. Close your eyes and turn your head side to side. You know that your head is moving, even without a visual cue. Part of this is due to proprioceptive receptors in your neck, but the other part is due to the angular acceleration your inner ear experiences during the movement. Cognition. Cognition refers to the basic mechanisms by which people perceive, think, and remember. This also refers to the limits of the human cognitive system: what we remember and forget, how we remember and forget, our attention spans, and how we interact with time. Human decision-making. Closely related to cognition is the concept of human decision-making and problem-solving. In fact, this concept is defined as high-level cognitive processes that use and interpret multiple pieces of information to select the best course of action. Because the information we process in order to make decisions may be simple or complex, and we're often deciding between various potential outcomes, decision-making is associated with uncertainty and risk. And in increasingly complex systems, decision-making becomes more difficult and prone to error, which makes decision-making a central concern in human factors. Stress. Unsurprisingly, stress has a major effect on human performance. Stressors can be either physical or psychological, but both lead to health risks and lowered performance.
And there you have it, a brief summary of the goals and considerations of human factors engineering.
Chapter 2. What are extreme environments?
Now that we have a basic understanding of human factors engineering, let's take a look at extreme environments and talk about why outer space and the deep ocean are so dangerous for humans. Extreme environments are defined as habitats that are considered very hard to survive in due to certain dangerous conditions, such as extreme pressure, temperature, or toxicity. There are several different types of extreme environments, including alkaline or acidic, extremely cold or extremely hot, hypersaline, under pressure, high levels of radiation, without water, and without oxygen, just to name a few. So why is outer space considered extreme? Turns out the list is very long. According to NASA, even staying close to Earth in low Earth orbit can be very dangerous. This is because the conditions in outer space pose a threat both to human life, but also to the materials that make up spaceships that allow us to go there. These conditions include exposure to the ultra vacuum, to extreme heat and extreme cold, free atomic oxygen, and high energy radiation. Additionally, constant bombardment by micrometeoroids can leave dents in vehicles. For astronauts, being in space means being exposed to varied and increased levels of radiation that are difficult to shield against. Astronauts must also deal with isolation and confinement, as well as communication delays and high levels of system independence that result from being far away from Earth. The human body is also greatly affected by microgravity. Without gravity, humans quickly lose muscle and bone density, requiring carefully planned diets and lots of exercise while in space. Also affected by the loss of gravity is the vestibular system, which, if you recall, is responsible for the body's understanding of direction and balance. It takes astronauts time to adjust to being in outer space, as the lack of up and down in outer space throws off the vestibular system. This affects spatial retention, hand-eye coordination, balance, and locomotion, and can cause motion sickness. There are many other elements that make outer space so dangerous, but I hope this summary shows why it's so extreme. But what about the deep ocean? It's about as far away from outer space as you can get, but the conditions are no less forgiving. The deep ocean is any point in the ocean that is below 200 meters in depth. At these depths, the environment is extremely harsh, with temperatures below 5 degrees Celsius, pressures at 200 times normal atmospheric pressure, no sunlight, and of course, no breathable air. The conditions in the deep ocean are so intense that until the late 19th century, many people thought that the ocean was too extreme to support life. As you descend from the surface of the ocean, the water pressure increases by 1 atmosphere for every 10 meters descended. Recreational scuba divers tend to go down only to 18 meters, so it is clear to see why people need the support of technology to go down even further. Now we know that in addition to the difficulties in getting to outer space or the deep ocean, it is also impossible for people to live there without technology creating a habitable zone within these extreme environments. And the key to designing those technologies that can support human life in these places is, of course, human factors engineering. So let's now take a look at 2 case studies that have allowed people to explore outer space and the deep ocean.
Chapter 3. The International Space Station. 250 miles above the Earth, in low Earth orbit, circles the International Space Station, also known as the ISS. The station is one big research platform that has sustained continuous human presence in outer space for over 20 years. Its goal is to perform research to improve life on Earth, enable future space exploration, and understand the universe. Fortunately, learning about the human factors design process NASA used to create the ISS is easy, since NASA keeps really good records about their work. Firstly, NASA adheres to its own standards. Among these, the NASA Standard 3000 document, which is 331 pages of specifications, guides, and tests to ensure that all mechanisms and systems in the ISS comply to human factors specialist standards. The document goes over systems engineering processes and requirements, physical characteristics and capabilities, perception and cognition, natural and induced environments, habitability functions, architecture, hardware and equipment, human performance and crew interfaces, spacesuits, ground assembly design, and emergency egress operations. This standard is one of many that ensures space technology is designed and tested correctly, but this one provides a broad overview of what goes into ISS tech. For some of the actual design considerations used to build the ISS, we can turn to Human Factors and the International Space Station, a document from the NASA Johnson Space Center. For some highlights, the spatial design of the ISS was constrained by the challenges of carrying modules into orbit using the Space Shuttle, restricting size and shape. Inside the modules, special consideration was given to how the human body changes in space, from spine elongation to muscle and strength reductions to posture and stability. Modules were also designed with the lack of gravity and direction in mind, utilizing all wall space without requiring a specific floor or ceiling. The ISS uses supplemental lighting and interior volume control to maintain a regular circadian rhythm for astronauts, as their orbit creates a 90-minute day-night cycle. To maximize crew members' time, they follow detailed daily schedules that keep them on track and in communication with the ground each day. This is also all done with the support of international partners, as NASA is not the only agency that uses the ISS. Chapter 4: The DSV Limiting Factor. The deep ocean and outer space may seem very different, but the capsules required to sustain human life actually face similar challenges. Both are environments with extreme external pressure and a lack of breathable oxygen. In fact, even the effects of being in outer space without a spacesuit and surfacing too quickly when scuba diving are remarkably similar. So, naturally, the part of the ocean that seems to fascinate people the most is the very deepest point. The Mariana Trench is famously deep, and Challenger Deep, a part of the Mariana Trench, is the deepest known point in the entire ocean. It reaches depths of nearly 11,000 meters, with pressures of about 1,000 atmospheres. In 2019, American private equity investor, author, retired naval officer, climber of Mount Everest, explorer, aquanaut, and astronaut Victor Vescovo set a number of records by diving to the very bottom of Challenger Deep in his submersible, the DSV Limiting Factor. The sub was designed with the human crew in mind, as its goal was to enable repeatable journeys to the ocean's deepest point. Designed by the company Triton, the Limiting Factor is the world's first and only manned submersible that is able and certified to dive down to full ocean depth. The submarine's design was kept simple and refined to minimize complexity, including the design of onboard systems, layout of pilot controls, and handling on the surface. The vehicle included viewports that offer the pilot uncompromised downward and forward views to increase situational awareness. It was designed with reliability as a priority. The sub has a titanium exterior with acrylic viewports, and the pilot's sphere was machined to 99.933% of true spherical form to allow for even pressure distribution. The Limiting Factor is also equipped with a robotic manipulator arm and lots of cameras and lights.
Thank you so much for sticking around until the end of this video. I hope you learned something new about human factors engineering, outer space, or the deep sea. In the description box below this video, you'll find all of the sources I used in this video, as well as lists for further reading. Thanks again for watching, and have a great day.